19 deals with thermodynamics. Okay, we've already done a chapter on thermodynamics way back a while ago. A long time ago.
December 7th.
Exactly.
1992.
Okay, so for 19 now we're looking at more with thermodynamics, and it'll be heat and entropy and things like that. We're also going to look at spontaneity and Gibbs free energy and reactions and stuff like that. So
I remember spontaneous.
the first thing I look at is the first law of thermodynamics, okay, which is really easy. Just is that energy is always conserved. Okay, for our first law, we're talking about energy just being conserved. It has nothing to do with how much of the reaction happens, just that energy is always transferred from one place to another, whether it's in the form of mechanical energy or electrical energy or chemical energy, potential, kinetic, whatever. Energy is always just transferred from one spot to another spot. Huh? The battery died. Okay, so easy stuff. We're talking about spontaneous reactions. Okay, spontaneous reactions are a process that occurs without any outside intervention. It means it just goes. Okay, if I want to try and decompose salt into sodium and chloride, it will not happen. Okay, but I can readily get sodium and chlorine to combine to make salt. So a spontaneous reaction is one that just occurs without any outside help. Other examples that they gave is bricks will just going to fall. If I have my airliner on my desk here, eventually if I get it on the edge, it's just going to fall. Okay, it's not going to just stay hovering in midair. Okay, that's a spontaneous reaction. It just happens. I don't have to do anything to get it to go there. Ice just melts. That's spontaneous. Okay, spontaneous reactions have a definite direction. Okay, they are spontaneous one direction, but non-spontaneous the other. Spontaneous depends on temperature. Like I just gave an example of water to ice at room temperature is non-spontaneous, but ice to water is very spontaneous. Okay, predict whether the following processes are spontaneous as described. Whether they are spontaneous in the reverse direction or whether they're spontaneous at equilibrium. So if I have a piece of metal heated to 150 degrees Celsius is added to water at 40, my water gets hotter. Is that spontaneous or non-spontaneous?
Non-spontaneous. Spontaneous.
Thank you. Spontaneous. That is just going to happen. The water is just going to heat up. I don't have to do anything to get my water to get hotter because the metal is hotter, so the metal will heat up the water. B, water at room temperature decomposes into H2 and O2.
None.
None, that's not going to happen. Water is not just going to fall apart. You have to run electricity through it to get it to split apart. Okay, benzene vapor at a pressure of 1 atmosphere condenses to liquid at a normal boiling point of 80.1 degrees Celsius. Okay, what this is saying is that my benzene vapor condenses.
Spontaneous in equilibrium.
It is spontaneous in equilibrium. Okay, if you're seeing some criteria for spontaneity, loss of energy is a common feature of something that is spontaneous. They're not always exothermic, but they are a lot of times. Okay, you can look at ways in which a state of your system can change, whether from a solid to a liquid or liquid to a gas. You can look at state functions, depending on how you get there. You can look at work and heat. Okay, remember with state functions that we have where it doesn't depend on how you get there, but that you get there. All right, and the amount of work that can be extracted from a spontaneous process depends on the way the process is done. So we're talking about something that is spontaneous. You can look at all those lovely things. Okay, now we're looking at reversible and irreversible processes. Something is reversible. Okay, that means that I have some kind of system where I can restore them to their original state once I make a change. You have to be exactly reversing your change. It has to be exact. You have to do what I did to get there, I have to undo exactly. You can't change what you're doing for it to be reversible. Okay? So that, but with these, there is no net change in either your surroundings or your system. Nothing changes. I undid what I just did. If I have 1 atmosphere at 0 degrees Celsius, if I have ice to liquid, okay, if I go ice to liquid, I need to add heat to get it to do that, right? So I add heat to get it to go from an ice to a liquid. I need to add, or remove, I'm sorry, that same amount of heat to get my liquid to go back to my ice. So whatever amount of heat I added to go this way, I have to add or remove, I'm sorry, I can say add. I need to remove the same amount of heat to go the other direction. Irreversible processes are just what they sound like. They cannot simply be reversed and restore their system to the exact original state. Okay, you have to take a different path to get the process back to where it was. Okay, I move this partition in between these two. Okay, as soon as you move the partition, it's spontaneous. This gas that's in here is going to spread out. That's a spontaneous process. Okay, in order to get it shoved back to the other side, I can't just put the partition back down again. That's not going to work because I'm going to end up with half of the gas on one side, half of it on the other. So if you take a top, okay, a piston, you push it in, and it'll push all of that over, and then I can get it all on that side. But that's a different path than I originally took the first time. Terminology-wise, if you ever see, and sometimes I like to put these words in here, if you ever see the word isothermal, put the two together, same temperature. If I say some kind of process is isothermal, that just means I have a constant temperature or the same temperature. Iso, same, thermal, temperature. Okay, other. If you have a system in equilibrium, if I have something with equilibrium, that means my reactants and products convert reversibly. They go back and forth. Equilibrium reactions are reversible reactions. The other notes put here is that any spontaneous reaction when flipped is non-spontaneous. So anything that is spontaneous is irreversible. All spontaneous reactions are irreversible because if I flip it, it's non-spontaneous, which means it won't go the same direction that the same path that I had before. Entropy. Entropy is associated with the randomness of a system.
It's the opposite of
Entropy.
entropy.
Yeah.
There are much better definitions for entropy, but
What is that?
I don't get into them. Randomness of a system. It's the extent to which energy is distributed or dispersed. Okay, entropy is an uppercase S. It is a state function as well, but it's also an S. You see S somewhere or delta S, that is entropy. And like I said, there are better definitions for entropy, but I will leave that to somebody at another class. Okay, second law, last couple things here. Second law of thermodynamics. Entropy indicates whether a process is spontaneous or not. So we can use entropy to tell whether something is going to be spontaneous. If I have a positive S, that means my final is more disordered than initial.
Oh, good times. Yeah, the same page.
So when we talk about entropy, we talk about randomness. Yeah. When we talk about this, we talk about more order or less order, or more random or less random. Like I said, there are other definitions for that, but you can learn that when you go off to college. Right now, this is the easiest one. Way to put this. If it's a positive S, it's more disordered. If it's a negative S, it's less disordered. Gases have a higher entropy than solids. Gases are way more unordered than a solid. Okay, there are three laws of thermodynamics that we look at. Okay, here is the second one. This is that any irreversible process results in overall increase in entropy. So the entire entropy of the universe increases for any irreversible process. Okay? Since all what we call kind of real processes are irreversible and spontaneous, that means that the total entropy of my entire universe goes up anytime you have an irreversible process. If I produce orders, if I decrease my S for a system, okay, I cannot proceed without producing an equal disorder or increase in my surroundings. So if I produce some kind of decrease in S for a system, that increases the S for my surroundings. So if my system becomes less disordered or more ordered, my surroundings become more disordered. It's just how it goes. Your system is whatever you're looking at. Your surroundings is whatever surrounds it. So whatever you dictate as this is my system, the rest of it's everything else is my surroundings.